A rivet is a permanent mechanical fastener. Before being installed, a rivet consists of a smooth cylindrical shaft with a head on one end. The end opposite the head is called the buck tail. On installation, the rivet is placed in a punched or drilled hole, and the tail is upset, or bucked, so that it expands to about 1.5 times the original shaft diameter, holding the rivet in place. To distinguish between the two ends of the rivet, the original head is called the factory head and the deformed end is called the shop head or buck tail. Because there is effectively a head on each end of an installed rivet, it can support tension loads. However, it is much more capable of supporting shear loads. Bolts and screws are better suited for tension applications. Fastenings used in traditional wooden boat building, such as copper nails and clinch bolts, work on the same principle as the rivet but were in use long before the term rivet was introduced and, where they are remembered, are usually classified among nails and bolts respectively. Types. There are a number of types of rivets, designed to meet different cost, accessibility, and strength requirements. Solid round-head rivets. Solid rivets are one of the oldest and most reliable types of fasteners, having been found in archaeological findings dating back to the Bronze Age. Solid rivets consist simply of a shaft and head that are deformed with a hammer or rivet gun. A rivet compression or crimping tool can also deform this type of rivet. This tool is mainly used on rivets close to the edge of the fastened material, since the tool is limited by the depth of its frame. A rivet compression tool does not require two people, and is generally the most foolproof way to install solid rivets. Solid rivets are used in applications where reliability and safety count. A typical application for solid rivets can be found within the structural parts of aircraft. Hundreds of thousands of solid rivets are used to assemble the frame of a modern aircraft. Such rivets come with rounded or 100-degree countersunk heads. Typical materials for aircraft rivets are aluminium alloys, titanium, and nickel-based alloys. Some aluminum alloy rivets are too hard to buck and must be softened by annealing prior to being bucked. Icebox aluminum alloy rivets harden with age, and must likewise be annealed and then kept at sub-freezing temperatures to slow the age-hardening process. Steel rivets can be found in static structures such as bridges, cranes, and building frames. The setting of these fasteners requires access to both sides of a structure. Solid rivets are driven using a hydraulically, pneumatically, or electromagnetically driven squeezing tool or even a handheld hammer. Applications where only one side is accessible require blind rivets. High-strength structural steel rivets. Until relatively recently, structural steel connections were either welded or riveted. High-strength bolts have largely replaced structural steel rivets. Indeed, the latest steel construction specifications published by AISC no longer covers their installation. The reason for the change is primarily due to the expense of skilled workers required to install high-strength structural steel rivets. Whereas two relatively unskilled workers can install and tighten high-strength bolts, it takes a minimum of 4 highly skilled riveters to install rivets in one joint at a time. At a central location near the areas being riveted, a furnace was set up. Rivets were placed in the furnace and heated to a glowing hot temperature. The rivet warmer or heater used tongs to individually remove rivets and throw them to a catcher station near the joints to be riveted. The catcher caught the rivet in a leather or wooden bucket with an ash-lined bottom, placed the glowing hot rivet into the hole to be riveted, and then quickly turned around to await the next rivet. The holder-up or holder-on would then hold a heavy rivet set or dolly or another pneumatic hammer against the round head of the rivet, while the riveter applied a pneumatic rivet hammer to the unformed head, making it mushroom tightly against the joint in its final domed shape. Before the use of pneumatic hammers, for example in the construction of RMS Titanic, the man who hammered the rivet was known as the basher. Upon cooling, the rivet contracted and exerted further force, tightening the joint. The last commonly used high-strength structural steel rivets were designated ASTM A502 Grade 1 rivets. Such riveted structures may be insufficient to resist seismic loading from earthquakes if the structure was not engineered for such forces, a common problem of older steel bridges. This is due to the fact that a hot rivet cannot be properly heat-treated to add strength and hardness. In the seismic retrofit of such structures, it is common practice to remove critical rivets with an oxygen torch, precision ream the hole, and then insert a machined and heat-treated bolt. Semi-tubular rivets. Semi-tubular rivets are similar to solid rivets, except they have a partial hole at the tip. The purpose of this hole is to reduce the amount of force needed for application by rolling the tubular portion outward. The force needed to apply a semi-tubular rivet is about 1/4 of the amount needed to apply a solid rivet. Tubular rivets can also be used as pivot points since the swelling of the rivet is only at the tail. Solid rivets expand radially and generally fill the hole, limiting movement. The type of equipment used to apply semi-tubular rivets range from prototyping tools to fully automated systems. Typical installation tools are handset, manual squeezer, pneumatic squeezer, kick press, impact riveter, and finally PLC-controlled robotics. The most common machine is the impact riveter, and the most common use of semi-tubular rivets is in lighting, brakes, ladders, binders, HVAC ductwork, mechanical products, and electronics. They are offered from 1/16 inch to 3/8 inch in diameter and can be up to 8 inches long. A wide variety of materials and platings are available. Most common base metals are steel, brass, copper, stainless, aluminum, and most common platings are zinc, nickel, brass, tin. Tubular rivets are normally waxed to facilitate proper assembly. An installed tubular rivet has a head on one side, with a rolled over and exposed shallow blind hole on the other. Semi-tubular rivets are the fastest way to rivets in mass production, but require capital investment. Blind rivets. Blind rivets, commonly referred to as pop rivets, are tubular and are supplied with a mandrel through the center. The rivet assembly is inserted into a hole drilled through the parts to be joined, and a specially designed tool is used to draw the mandrel into the rivet. This expands the blind end of the rivet and then the mandrel snaps off. These types of blind rivets have non-locking mandrels and are sometimes avoided for critical structural joints because the mandrels may fall out, due to vibration or other reasons, leaving a hollow rivet that has a lower load carrying capability than solid rivets. Furthermore, because of the mandrel, they are more prone to failure from corrosion and vibration. Unlike solid rivets, blind rivets can be inserted and fully installed in a joint from only one side of a part or structure, blind to the opposite side. Prior to the adoption of blind rivets, installation of a solid rivet typically required access to both sides of the assembly, a rivet hammer on one side and a bucking bar on the other side. In 1916, Royal Navy reservist and engineer Hamilton Neil Wiley filed a patent for an improved means of closing tubular rivets. In 1922, Wiley joined the British aircraft manufacturer Armstrong Whitworth Limited to advise on metal construction techniques. Here he continued to develop his rivet design with a further 1927 patent that incorporated the pull-through mandrel, and allowed the rivet to be used blind. By 1928, the George Tucker Eyelet Company produced a cup rivet based on the design. It required a separate GKN mandrel and the rivet body to be hand-assembled prior to use for the building of the Siskin 3 aircraft. Together with Armstrong Whitworth, the Geo Tucker Company further modified the rivet design to produce a one-piece unit incorporating mandrel and rivet. This product was later developed in aluminium and trademarked as the POP rivet. The United Shoe Machinery Company produced the design in the U.S. as inventors such as Carl Cherry and Lew Huck experimented with other techniques for expanding solid rivets. Due to this feature, blind rivets are used mainly when access to the joint is available from only one side. The rivet is placed in a drilled hole and is set by pulling the mandrel head into the rivet body, expanding the rivet body and causing it to flare against the reverse side. As the head of the mandrel reaches the face of the blind side material, the pulling force is resisted, and at a predetermined force, the mandrel snaps at its break point, also called blind setting. A tight joint formed by the rivet body remains, the head of the mandrel remains encapsulated at the blind side, although variations of this are available, and the mandrel stem is ejected. They are available in flat head, countersunk head, and modified flush head with standard diameters of 1/8, 5/32 and 3/16 inch. Blind rivets are made from soft aluminum alloy, steel, copper, and monal. There are also structural blind rivets, which are designed to take shear and tensile loads. The rivet body is normally manufactured using one of three methods. There is a vast array of specialty blind rivets that are suited for high-strength or plastic applications. Typical types include, internally and externally locked structural blind rivets can be used in aircraft applications because, unlike other types of blind rivets, the locked mandrels cannot fall out and are watertight. Since the mandrel is locked into place, they have the same or greater load-carrying capacity as solid rivets and may be used to replace solid rivets on all but the most critical stressed aircraft structures. The typical assembly process requires the operator to install the rivet in the nose of the tool by hand and then actuate the tool. However, in recent years automated riveting systems have become popular in an effort to reduce assembly costs and repetitive disorders. The cost of such tools range from $1,500 for auto-feed pneumatics to $50,000 for fully robotic systems. Oscar rivets. Oscar rivets are similar to blind rivets in appearance and installation, but have splits along the hollow shaft. These splits cause the shaft to fold and flare out as the mandrel is drawn into the rivet. This flare provides a wide-bearing surface that reduces the chance of rivet pullout. This design is ideal for high-vibration applications where the back surface is inaccessible. Drive rivet. A drive rivet is a form of blind rivet that has a short mandrel protruding from the head that is driven in with a hammer to flare out the end inserted in the hole. This is commonly used to rivet wood panels into place since the hole does not need to be drilled all the way through the panel, producing an aesthetically pleasing appearance. They can also be used with plastic, metal, and other materials and require no special setting tool other than a hammer and possibly a backing block placed behind the location of the rivet while hammering it into place. Drive rivets have less clamping force than most other rivets. Drive screws, possibly another name for drive rivets, are commonly used to hold name plates into blind holes. They typically have spiral threads that grip the side of the hole. Flush rivet. A flush rivet is used primarily on external metal surfaces where good appearance and the elimination of unnecessary aerodynamic drag are important. A flush rivet takes advantage of a countersink hole. They are also commonly referred to as countersunk rivets. Countersunk or flush rivets are used extensively on the exterior of aircraft for aerodynamic reasons. Additional post-installation machining may be performed to perfect the airflow. Friction lock rivet. These resemble an expanding bolt except the shaft snaps below the surface when the tension is sufficient. The blind end may be either countersunk or dome-shaped. One early form of blind rivet that was the first to be widely used for aircraft construction and repair was the cherry friction lock rivet. Originally, cherry friction locks were available in two styles, hollow shank pull-through and self-plugging types. The pull-through type is no longer common, however. The self-plugging cherry friction lock rivet is still used for repairing light aircraft. Cherry friction lock rivets are available in two head styles, universal and 100-degree countersunk. Furthermore, they are usually supplied in three standard diameters, 1/8, 5/32 and 3/16 inch. A friction lock rivet cannot replace a solid shank rivet, size for size. When a friction lock is used to replace a solid shank rivet, it must be at least one size larger in diameter because the friction lock rivet loses considerable strength if its center stem falls out due to vibrations or damage. Rivet alloys, shear strengths, and driving condition. Self-pierce rivets. Self-pierce riveting is a process of joining two or more materials using an engineered rivet. Unlike solid, blind and semi-tubular rivets, self-pierce rivets do not require a drilled or punched hole. SPRs are cold forged to a semi-tubular shape and contain a partial hole to the opposite end of the head. The end geometry of the rivet has a chamfered poke that helps the rivet pierce the materials being joined. A hydraulic or electric servo rivet setter drives the rivet into the material, and an upsetting die provides a cavity for the displaced bottom sheet material to flow. The self-pierce rivet fully pierces the top sheet material, but only partially pierces the bottom sheet. As the tail end of the rivet does not break through the bottom sheet, it provides a water or gas-tight joint. With the influence of the upsetting die, the tail end of the rivet flares and interlocks into the bottom sheet, forming a low-profile button. Rivets need to be harder than the materials being joined. They are heat-treated to various levels of hardness depending on the material's ductility and hardness. Rivets come in a range of diameters and lengths depending on the materials being joined. Head styles are either flush countersunk or pan heads. Depending on the rivet setter configuration, that is hydraulic, servo, stroke, nose-to-die gap, feed system etc., cycle times can be as quick as 1 second. Rivets are typically fed to the rivet setter nose from tape and come in cassette or spool form for continuous production. Riveting systems can be manual or automated depending on the application requirements. All systems are very flexible in terms of product design and ease of integration into a manufacturing process. SPA joins a range of dissimilar materials such as steel, aluminum, plastics, composites and pre-coated or pre-painted materials. Benefits include low energy demands, no heat, fumes, sparks or waste and very repeatable quality. Sizes. Although there are a plethora of specifications, most rivets come in 2 basic flavors: imperial units with diameters such as 1/8 or 5/16. System E International or SI units with more readily understood diameters such as 3 mm, 8 mm, and these have been adopted in Europe and in many emerging countries. The main official standards relate more to technical parameters such as ultimate tensile strength and surface finishing than physical length and diameter. They are: imperial rivet diameters are commonly measured in 1/32-inch increments and their lengths in 1/16-inch increments, expressed as dash numbers at the end of the rivet identification number. A -3-4 designation indicates a 3/32-inch diameter and 4/16-inch length. Some rivets lengths are also available in half sizes, and have a dash number such as a Euro 3.5 to indicate they are half size. The letters and digits in a rivet's identification number that precede its dash numbers indicate the specification under which the rivet was manufactured and the head style. On many rivets, a size in 32 NDS may be stamped on the rivet head. Other makings on the rivet head, such as small raised or depressed impulse or small raised bars, indicate the rivet's alloy. To become a proper fastener, a rivet should be placed in hole ideally for a Euro 6/1000 of an inch larger in diameter. This allows the rivet to be easily and fully inserted, then setting allows the rivet to expand, tightly filling the gap and maximizing strength. Metric rivet diameters and lengths are measured in millimeters. Conveniently, the rivet diameter relates to the drill required to make a hole to accept the rivet, rather than the actual diameter of the rivet, which is slightly smaller. This facilitates the use of a simple drill gauge to check both rivet and drill are compatible. For general use, diameters between 2 mm-20 mm and lengths from 5 mm-50 mm are common. The design type, material and any finish is usually expressed in plain language. Applications. Before welding techniques and bolted joints were developed, metal-framed buildings and structures such as the Eiffel Tower, Schuylkill Tower and the Sydney Harbour Bridge were generally held together by riveting. Also automobile chassis were riveted. Riveting is still widely used in applications where lightweight and high strength are critical, such as in an aircraft. Many sheet metal alloys are preferably not welded as deformation and modification of material properties can occur. Rivets were also used in many tanks during World War II by a large number of countries including the M3 Lee manufactured in the United States. However, many countries soon learned that rivets were a large weakness in tank design, since if a tank was hit by a large projectile it would dislocate the rivets and they would fly around the inside of the tank and injure or kill the crew, even if the projectile didn't penetrate the armor. Some countries such as Italy, Japan, and Britain used rivets in some or all of their tank designs throughout the war for various reasons, such as lack of welding equipment or inability to weld very thick plates of armor effectively. Blind rivets are used almost universally in the construction of plywood road cases. Common but more exotic uses of rivets are to reinforce jeans and to produce the distinctive sound of a sizzle cymbal. Joint analysis. The stress and shear in a rivet is analyzed like a bolted joint. However, It is not wise to combine rivets with bolts and screws in the same joint. Rivets fill the hole where they are installed to establish a very tight fit. It is difficult or impossible to obtain such a tight fit with other fasteners. The result is that rivets in the same joint with loose fasteners carry more of the load, they are effectively more stiff. The rivet can then fail before it can redistribute load to the other loose-fit fasteners like bolts and screws. This often causes catastrophic failure of the joint when the fasteners unzip. In general, a joint composed of similar fasteners is the most efficient because all fasteners reach capacity simultaneously. Installation: solid and semi-tubular rivets. There are several methods for installing solid rivets. Manual with hammer and handset or backing bar, pneumatic hammers, handheld squeezers, riveting machines, pin hammer, rivet set. Rivets small enough and soft enough are often bucked. In this process the installer places a rivet gun against the factory head and holds a backing bar against the tail or a hard working surface. The backing bar is a specially shaped solid block of metal. The rivet gun provides a series of high impulse forces that upsets and work hardens the tail of the rivet between the work and the inertia of the backing bar. Rivets that are large or hard may be more easily installed by squeezing instead. In this process a tool in contact with each end of the rivet clinches to deform the rivet. Rivets may also be upset by hand, using a ball-peen hammer. The head is placed in a special hole made to accommodate it, known as a rivet set. The hammer is applied to the buck tail of the rivet, rolling an edge so that it is flush against the material. Testing: solid rivets for construction. A hammer is also used to ring an installed rivet, as a non-destructive test for tightness and imperfections. The inspector taps the head of the rivet with the hammer while touching the rivet and base plate lightly with the other hand and judges the quality of the audibly returned sound and the feel of the sound traveling through the metal to the operator's fingers. A rivet tightly set in its hole returns a clean and clear ring, while a loose rivet produces a recognizably different sound. Testing of blind rivets. A blind rivet has strength properties that can be measured in terms of shear and tensile strength. Occasionally rivets also undergo performance testing for other critical features, such as push-out force, break load and salt spray resistance. A standardized destructive test according to the inch fastener standards is widely accepted. The shear test involves installing a rivet into two plates at specified hardness and thickness and measuring the force necessary to shear the plates. The tensile test is basically the same, except that it measures the pull-out strength. Per the IFI 135 standard, all blind rivets produced must meet this standard. These tests determine the strength of the rivet, and not the strength of the assembly. To determine the strength of the assembly, a user must consult an engineering guide or the machinery's handbook. Alternatives. See also: Cleco, Clinker, Rivet Nut, Rosie the Riveter. References. Bibliography: Smith, Carroll. Carroll Smith's Nuts, Bolts, Fasteners, and Plumbing Handbook. Motor Books MBI Publishing Company. PA 112. ISBN A0-87938-406-9. External links: Popular Science, November 1941. Self-setting explosive rivet speeds warplane building system used by both the US and Germany in World War II for aircraft assembly. See bottom half of page. 4 methods of flush riveting film made by Disney Studios during World War II. Hold Everything, February 1946. Popular Science. New rivet types developed during World War II. Blind rivets, they get it all together. Popular Science, October 1975. PPA 126 €128. RMS Titanic remembered, The Lads in the Shipyard.